Hi everybody, welcome back to the channel. In this video we're going to take a look at some examples of using L'Hopital's rule and solving for indeterminate forms. Let's go ahead and jump right in. We have 4 different examples. I'm going to hope we have enough time to get to all of them. So the first one we're going to be looking at looks like the limit as x goes to infinity of e to the x over x squared. And what we saw in the last video is that if when plugging in a value you have 0 over 0 or infinity over infinity, that's when we can go ahead and use L'Hopital's rule. And if you remember what L'Hopital's rule says, it says that we only care about looking at the derivative of the top and the derivative of the bottom if you get 0 over 0 or infinity over infinity. So in this case, if you think about plugging in infinity for x, e to the infinity is infinity, and infinity squared is infinity. That's a little informal language to talk about plugging in infinity. I think you know that, but the idea is we do get that value that we're looking for. And so what I said in the last video is that whenever I write an equals, I'm going to say LHR here so that I know why the next step works, and it's because of L'Hopital's rule. So L'Hopital's rule says take the derivative of the top. I still need my limit here, by the way. Still got to carry that along. So the limit as x goes to infinity of, let's see, this should be e to the x on the top, and then on the bottom is 2x. Now here's a problem with this. So that would be fine if we could plug in and kind of keep on going, but when you plug in infinity, you again get e to the infinity over 2 times infinity. You get infinity over infinity again. So sometimes we might have to use L'Hopital's rule more than one time in a problem. That's okay. We can keep on going. This is like saying find the second derivative of the original. But again, it's the derivative of the derivatives. Think about this as kind of your new function, and you're kind of just starting over and doing the process over again. And so this is equal to the limit as x goes to infinity of e to the x over 2. And hopefully you notice it on the top. If you kept doing this over and over and over again, you're always going to get e to the x on the top. And then on the bottom, eventually you're going to get down to having a constant. And so if you plug this in, now you get just infinity divided by 2, which is infinity as your answer. We know that you can get infinity as your answer when we're talking about limits there. That's not a problem. Okay, so this is kind of like the one we saw in the last video, where in the last video we had a situation of 0 over 0. We can do the same thing when we have infinity over infinity. Okay, remember all 5 of those indeterminate form cases we're trying to bring back to look like either 0 over 0 or infinity over infinity. So let's take a look at another situation where we don't have something like 0 over 0 or infinity over infinity. We actually have to change it a little bit first. And so if you think about kind of plugging in 0 here, it's from the right, because you're not allowed to plug in negative numbers into the natural log. So x goes to 0 from the right. But if you plug in 0, you get 0 times, and then the natural log of 0 is actually kind of like negative infinity. And so here's one of those cases where you get 0 times infinity, or in this case 0 times negative infinity. That's an indeterminate form. So what we want to do is we want to use some algebra to try to turn it into something that looks like 0 over 0. Here's what I would recommend. Let's go ahead and do this, where what we'd like to do is create a fraction. Remember, if you can have 0 over 0 or infinity over infinity, you need to have a fraction there somehow. So here's how we're going to create a fraction. I'm going to take this part, the x in the front, and I'm going to basically move that to the bottom of the fraction by making it 1 over. Okay, so this is going to be the natural log of x on the top, and then on the bottom it's going to be 1 over x, and that's exactly the same thing algebraically, just rewriting it in a little bit of a different way. Okay, now I'm not moving the natural log of x to the bottom because I think that would make it a lot more complicated. I'm just leaving it as a 1 over x on the bottom. To try to take the derivative of 1 over the natural log gets a little bit tricky. I'm not sure that helps us out as much as trying to flip the 1 over x on the bottom. Now, if you think about plugging in 0, now you end up getting, actually not 0, you end up getting infinity over infinity here. And so we're back to that situation that we just had in the last problem where we can use L'Hopital's rule here. Okay, so equals, there's my LHR saying I'm using L'Hopital's rule. So the limit as x goes to 0 from the right. Now take the derivative of the top and the derivative of the bottom. The derivative of the top is 1 over x. Let's see, the bottom, another way to write the bottom is to write it as x to the negative 1. So when I take the derivative of that, that's negative x to the negative 2, which is 1 over x squared. Okay, I can simplify this a little bit and just use some algebra here. If I think about flipping the 1 over x squared and multiplying, so another way to write this is 1 over x times x squared over 1. This should be a negative from the bottom, and I'm still talking about the limit as x goes to 0 from the right. I'm not sure why I'm writing it small like this over here. I think to save myself some space over here, and so when you cancel an x on top and on bottom, you're going to be left with just an x on the top, and when you plug in 0 for x from the right over here, you're going to get an answer of this whole thing is equal to 0. And technically really a negative 0, but negative 0 doesn't make any sense. It's actually just 0. So this is my recommendation anytime you have a problem where you have 0 times infinity, is to try to flip one of your factors and move it to the bottom so that you create a fraction, and that's 0 over 0 or infinity over infinity. Okay, let's take a look at the next example. In this example, we have something like the limit as x goes to infinity of e to the x minus x. This is the situation where if you plug in a value, you end up getting something like infinity minus infinity. This was another one of our indeterminate forms, and again, we can't really just deal with this as taking the derivative of one piece and the derivative of the other until we have a fraction that looks like 0 over 0 or infinity over infinity. By the way, a really common mistake I see is people want to take the derivative of both of the terms here and then try to deal with that, and it's like, well, that's not what L'Hopital's rule says. L'Hopital's rule says you have to have a fraction where it's 0 over 0 or infinity over infinity, then you can do that on top and on bottom. So just be careful. L'Hopital's rule doesn't just say take derivatives of everything everywhere and then try to deal with it. No, you need a fraction of 0 over 0 or infinity over infinity. Okay, so let's go ahead and see if we can kind of turn this in, algebraically turn this into something that looks like 0 over 0. So not doing L'Hopital's rule yet, just kind of using some algebra here. This is the limit as x goes to infinity. What I'm going to do is I'm going to factor something out. Okay, I'm going to factor out an x. So let's go ahead and factor out an x. It's going to look like this. If I factor out an x, factor out means divide, so what we end up getting at is something like this. We have e to the x over x divided by 1 on the inside after we factor out an x. You could check that by distributing the x back in and making sure you get exactly what you started with. Now, with this, you may remember a rule from our past that says something like this, that when we're taking the limit, not a derivative, we're taking the limit of a product. You don't need a product rule like for limits. That was just for derivatives. For limits, you can take the limit of each of the individual items separately and then multiply them together. Okay, so you can basically split it up as two separate limits like this. Again, I haven't used any derivatives yet. I haven't used L'Hopital's rule yet. I haven't used a ton of calculus yet other than to talk about a limit rule. And so we could look at what's happening here. The limit as x goes to infinity of x is just infinity. And then we can look at what happens with this piece right here. That's where L'Hopital's rule is going to come into play, because notice what you have here is the limit as x goes to infinity of e to the x over x. That's kind of like what we saw in one of the earlier examples, where that's infinity over infinity. And so that's where we can use L'Hopital's rule. And so that's going to end up being the same thing as the limit as x goes to infinity of, take the derivative of the top and the derivative of the bottom, and you get e to the x over 1. And then, by the way, that minus 1 has to stay on the end. Well, remember, we're not finding a derivative here. You can't say the derivative of 1 is 0. What we're really doing is splitting up the limit into both the fraction and into the 1 on the end and taking those limits separately. But the limit as x goes to infinity of 1 is just 1. So you got to actually leave that there. Okay. Now, when you look at the limit as x goes to infinity of e to the x over 1, that was actually coming from L'Hopital's rule. So we did actually use L'Hopital's rule in there to get from kind of this limit of a fraction down to talking about the limit as x goes to infinity of just e to the x over 1. Now, this looks a little bit crazy, but here's what we end up with. Infinity times, let's see, that limit is also infinity and then minus 1. Well, what happens when you have this really big number times a really big number and then take one away from it, you get infinity as your answer. Okay, so by the way, this is a common strategy whenever you have the situation of infinity minus infinity at the beginning, is factor something out. I could have factored out an e to the x. I don't know that that would have really changed the problem a lot. I think it would have made it exactly the same, basically. So not really a reason I chose to factor out an x instead of an e to the x. I think you basically end up with it pretty much the exact same way. So just something to consider there. Factor something out, and then you should end up with a fraction where it either looks like 0 over 0 or infinity over infinity. Okay, again, we're just trying to bring every case algebraically back to that 0 over 0 or infinity over infinity. All right, last example. Limit as x goes to 0 from the right of x to the x. This is a weird situation, okay? Let me point this out. We know how to deal with it if it looks like x squared. We know how to deal with it if it looks like 2 to the x, but x to the x is really weird. We haven't really seen that where you have variable both in the base and in the exponent. That is a weird case. Okay, and so if you were to plug in 0, I know it's talking about x going to 0 from the right. That's because it's we can't have a negative base there with a negative exponent, so that gets a little bit weird. That gets us into some complex number territory. So as x goes to 0 from the right, if you were to think about plugging in 0, you get 0 raised to the 0. That's that last case, that fifth case of our indeterminate form. And so we got to, again, algebraically think about how do we turn that back into something like 0 over 0 or infinity over infinity so that we can use L'Hopital's rule. So here's what that's going to look like. When we're dealing with an x in the base and in the exponent, that's tricky. So what I would recommend is rewriting it so that we get a different kind of level going on. The way we're going to do that is we're going to use logs and exponentials. Okay, so we can rewrite this. And so something you may remember is that if you have something like e to the natural log of x, you just get x, back from talking about properties of exponentials and logs. Or another way to write it is to write it as the natural log of e to the x is also just equal to x. And so you can rewrite x to the x as being e with a natural log or a natural log with an e. You can kind of take your pick there. It is going to work out either way. It's just going to be a little bit of different steps. What I'm going to choose to do, because of what we just saw in the last problem, is look at it like the first case, where it's e to the natural log of x to the x. Okay. Now, you also probably, I hope, remember rules about some logarithms and the way that those work. And one thing you may remember is that, so let me kind of put this in a box over here to say these are some past things you should remember. Another thing you should remember is that the natural log of b to the x is equal to x times the natural log of b. In other words, that exponent can drop down in front if you have a logarithm in there. Okay, so look at what we have up in the exponent now. We have e to the power of, and then we have a natural log of x raised to the x power. This is why you're going to always need to use logarithms or logarithms and exponentials whenever you have an x in the base and in the exponent, is because now when you have the natural log of x to the x, we have a rule that says that that exponent that's on the base inside of the natural log moves down into the front, multiplies by the natural log. So it looks like this, x times the natural log of x, all up in the exponent. Okay, now this is a good example for you to refer back to whenever you do see this case, because look at what we have up in the exponent, x times the natural log of x. That should look familiar to you. That was actually what we just had. Where was it? In our second example, the limit as x goes to 0 of x times the natural log of x. And do you remember what we got? Was we got 0. Okay, so this is like saying the limit as x goes to 0 from the right of e to the, well, that whole thing right there is supposed to be equal to 0. We know that. If you didn't know that, then you just walk through the steps of what we did in problem 2 again and just kind of repeat those steps. So otherwise, I would recommend referring back to that and kind of seeing what that looks like, but otherwise you would just do steps exactly like those. Okay, so here you go. E to the 0 is just 1. So that's what you get as your answer.